In example 4, we will consider the case where there are magnetic field and electric field together in the system. Okay, so the diagram here shows the Thomson's apparatus for measuring the charge to mass ratio, or this E to M of an electron. Okay, so an electron will have the charge of E and has a mass of M and has a negative charge. So the electron is accelerated from the cathode to the anode, or positive and negative electrode. Okay, so through a voltage V. Okay, so that we have the system that look like this. So we have the voltage V is a big V, and this big V is connecting the cathode and the anode. And if the electron has a charge E, the potential difference will give the potential energy of the electron to be E times V. So that is the potential energy, or U. Then the electron enters the region with perpendicular E field and B field, magnetic field and electric field, chosen such that electron move along a straight line. So when we say that electron is moving along a straight line like this, okay, so it is to say that if this negative charge electron has undergo a force from electric field, so if electric field going down and you have negative charge is going up, so Fe is going up. Okay, and for the magnetic field, you use the right hand rule, and you find that the magnetic field, the force from the magnetic field, or Fb, is in the downward direction. Okay, so the particle will go in a straight line in this axis. Okay, if and only if Fe and Fb is in equilibrium. Okay, so the force should be equal. So they ask you to prove that the ratio between charge and mass, or E over M, can be written in this form. Okay, so firstly, we will consider the first step of accelerating an electron. Okay, so we consider this region. Okay, so to do that, we use the conservation of energy again, so that we can write down the energy before, which is the potential energy U, and the energy after the acceleration, which is the kinetic energy K, when the electron moves. So the potential energy can be found from EV, and the kinetic energy when the electron moves can be found from half mv squared. Okay, and so that we have one relationship from the conservation of energy. And then we consider the equilibrium when your electron is moving in a straight line. Okay, so to do that, the force from magnetic field Fb need to be equal to the force from electric field, or Fe, and Fb can be written in terms of QVB in case that V, or velocity, is perpendicular to magnetic field. And for the magnitude of Fe, it is QE. Okay, when in this case Q is equals to E, or the charge of the electron, and we can cancel Q and E, and we have that the velocity can be written in terms of ratio between electric field and magnetic field. Okay, and then we just try to plug in this velocity into the conservation of energy we did before, so that we have EV equals to half m and times by E squared over B squared. Okay, and then I'll just rearrange the equation by move m to the left hand side, so that we have E over M, or the charge per mass, already And on this side, I come up with E square and then divided by 2VB square. And that is our answer. So it has been proved that E over M, or charge per mass ratio, can be written in terms of electric field, in terms of magnetic field, and in terms of the accelerating potential V.